So let's derive Kepler's third law, and I'm going to do it assuming circular orbits for simplicity, although Kepler's law can be derived from a much more general elliptical orbit. But I also want to work in the center of mass frame. So let me first explain what that is, or at least refresh you on the center of mass. So we're dealing with two objects orbiting in orbital motion. And let's say this has a mass m1, this has a mass m2, I'm labeling the objects 1 and 2. Then the center of mass is defined as the point between them, that is a distance r1 from the first object and a distance r2 from the second object, and the total distance we'll call r. This point here is such that m1 times r1 is equal to m2 times r2. The moments about this point here are equal, and therefore r1 divided by r2 is equal to m2 divided by m1. And we can check we've got this the right way round. We know intuitively that if m1 is more massive than m2, then the center of mass will be closer to m1, which means r1 should be smaller than r2. Well, this is what we find here. If m2 is smaller than m1, then r1 is smaller than r2. This ratio is less than 1. Okay, so let's do a quick estimate with a familiar orbital system, the Earth and the Moon. So the mass of the Moon is approximately 7 times 10 to the 22 kilograms, and the mass of the Earth is about 6 times 10 to the 24 kilograms. So just working to within an order of magnitude, the ratio, which is equal to the distance of the Earth from the center of mass divided by the distance of the Moon from the center of mass, is about 0.01. This is about 100 times smaller than this, which means that the center of mass is 100 times closer to the Earth than it is to the Moon. Well, the total separation of the Earth and Moon is round about 240,000 miles. And if the Earth is 100 times closer, that puts the distance of the center of mass from the center of the Earth at around 2,400 miles. Now, given that the radius of the Earth is approximately 4,000 miles, this means that the center of mass of the Earth-Moon system is actually inside of the Earth. Okay, this just reflects the fact that the Earth is so much bigger than the Moon. And a similar story holds for the Earth-Sun system. The mass of the Sun is about 1,000,000 times bigger than the mass of the Earth, which means the center of mass of the Earth-Sun system is going to be about 1,000,000 times closer to the Sun than it is to the Earth. Now, the Earth-Sun distance is about 10 to the 8 miles, and so the center of mass of the Earth-Sun system is only about 100 miles from the center of the Sun, and the Sun has a radius of about 1,000,000 miles, so it is way inside the atmosphere of the Sun. Now, of course, this isn't always the case. There are many objects we will encounter, particularly binary star systems, where the masses of the two objects are much closer. Okay, now if we were in the rest frame of mass 1, in other words, if we're sat on mass 1, whatever mass 1 is, then what we see is that mass 2 is going to be orbiting in a circle around it, and the center of masses will also be orbiting, tracking M2 as it orbits M1. Of course, if you then switch to M2, if we go to the Moon, then of course what we see is the Earth appears to go around the Moon. So if we are in the frame of reference of M2, M1 and the center of mass orbit M2. But we're going to work in the center of mass frame, which means we sit on the center of mass, and we are stationary with respect to the center of mass. In that case, what we see is mass 1 orbiting us and mass 2 orbiting us. Okay, so both these masses are going around orbiting the center of mass. They still have a total separation r. Let me relabel R1 and R2. Okay, so let me switch colors so we can see what's going on. Let me label the velocities of these two objects. So let's say this is V2, this is V1. And let me also label the forces they are exerting on each other. So mass 2 is pulling on mass 1 with a force, let's call it F21. And by Newton's third law, mass 1 is pulling on mass 2 with an equal and opposite force. Okay, so we have F12 is equal to minus F21. And we'll just call F12 F. And therefore this is minus F, just to save the markers. The forces are equal and opposite. However, because the masses are different, the accelerations each object experiences is going to be very different. Okay, this is, to take an extreme example, the force of the Earth pulling down on me is the same as the force of me pulling up on the Earth. Right, but when I jump into a swimming pool, my acceleration down towards the Earth is much greater than the Earth's acceleration up towards me, because I am much, much, much less massive than the Earth. So the accelerations in principle will be different, and the relative acceleration of the two objects is just the difference between acceleration 1 and acceleration 2. Now, we can plug in the forces into this equation here using Newton's second law. A2 is just going to be the force F12 divided by M2, and this is going to be F21 divided by M1. So that's the force F into 1 over M2 plus 1 over M1, right? Because F21 is minus F, whereas F12 is plus F. And putting this over a common denominator, M1, M2, we get M1 plus M2 on the top. And rearranging this, just moving this across to the left-hand side of the equation and calling it mu, we get Newton's second law in the center of mass frame. So the force on either of these objects is equal to the relative acceleration of the two objects times this quantity mu, which is equal to m1, m2 divided by m1 plus m2. And this is called the reduced mass of the system. Okay, now in the center of mass system, we can now use this formula together with, so this is Newton's second law. We haven't specified what this force is at the moment. We know it's gravity, so we have another law of physics for that tells us that the magnitude of this force is equal to g m1 m2 divided by r squared, the distance between them. Okay, so this is going to be equal to mu times a, where a is the magnitude of the relative acceleration. Now, the angular acceleration is equal to v squared over r, and the velocity or the speed of the orbit is just equal to the distance the object travels in its orbit, which is the circumference of the orbit. Again, remember, we're assuming a circular orbit at the moment for simplicity, divided by how long it takes to go once around the orbit, which is the period of the orbit. So plugging these two equations into the first one, we get g m1 m2 over r squared is equal to mu times a is v squared, which is 4 pi squared r squared divided by p squared, and then we're dividing by r. Okay, so this r cancels one of these r's, and we can move the remaining, or we can multiply both sides by r squared, and we get g m1 m2 is equal to mu times 4 pi squared r cubed divided by p squared. And we can see now we're pretty much here because all of these things are constants except r and p, which have this ratio r cubed over p squared, which is Kepler's law. Let's just complete this derivation. Mu is m1 m2 over m1 plus m2. So the product M1 and M2 cancels on both sides. We can multiply by M1 plus M2 and divide by 4 pi squared.
And we end up with r cubed is equal to big G over 4 pi squared times M1 plus M2 p squared. Okay, this is Kepler's third law, in that r cubed is proportional to p squared, but we have, by adding physics in, we have found that the constant of proportionality contains the mass of the system, and therefore, by observing the period and measuring the size of the orbit, one can extract the mass of astronomical systems.